Swayam Prabha. Digital India. Educated India.
And the future research is on all. Solid state physics. Now, when you say research in solid state physics, research in all these topics. How do you understand them? So let me bring one by one. All of you know magnetism. What is magnetism? From where the magnet is formed? Electrons, you know, charge transport. Right? Electron has a charge, it keeps moving, right? Just now we learned that there are three quantum numbers, N, L, and Ma and Ms or something. L is orbit. Ms is spin. The magnet is formed by primarily spin of L. We no longer define the electron by its charge. Correct? We no longer define the electron by its charge. We also define the electron by its spin, by its orbital quantity. If we can develop a scheme, or if we can develop new idea, so that the orbital quantum number of the electron can be exploited to tailor the transport properties. Do you get it? The orbital quantum number of the electron can be exploited to tailor the transport properties. That will be called orbitronics. Similarly, if spin of the electron can be exploited to tune the transport behavior, that is called spintronics. These two will come next. All of you have heard about quantum computers? What is that? Qubits. What is qubit? See, in quantum computers, you try to look for two binary states, which you call 1 and 0, or 1 and -1, or this and that, and try to make a superposition of this binary state to create more number of states. Right? Now we are storing data in 1 and 0. Now you can create superposition of these states, create more number of states, so you can store data in more number of states instead of 1 and 0. That's the whole philosophy of quantum computing, right? But for that you have to create a binary state like on and off. 1, 0 people say. Spins are the best binary state. In half, spin minus. So if you can design quantum computers with well-defined binary states, spin half and spin minus half, that will be so useful for quantum computers. That's why spintronics is important. All your memory devices, all of you say I have 3 GB, 4 GB this memory devices. How does the memory device work? Memory device works based on spin. One spin is half 1 and other is treated 0. So how much you can store depending on how many spins you are independent spin states are created. I'll tell you, when I was a student, I'm talking about how many years? 25, 30 years ago, they used to have this floppy drive. Have you heard about floppy drive? What is that? There's a big thin something half of this book size, right? And how much memory does it store? 3 megabyte. Huh? Floppy drive like a thin black sheet. You enter inside the index. 3 megabyte. Imagine a floppy drive. I don't have a picture of floppy drive, but you can browse in your mobile phone and see what is floppy drive. It's like a thin piece of sheet. You enter it. It can store 3 megabyte. Because at that time we didn't have developed materials where you can have a high density memory. Means highly dense spin states are injected. Now after floppy drive, what came into the market? CD, all of you know, compact disc. Compact discs are little better. Compact discs are like they can be 500 megabyte or something. Okay? Now what you guys are doing? Pen drive, you have seen, you have a tiny things, it can store 4, 5, 6 gigabyte. Nowadays there have been coming up with ideas how to store 64 gigabyte pen drives are also there. This is because they keep on developing finer materials. They do research and keep on developing finer materials where highly dense spin states are available. That's the domain of speed. We still are trying to make our computer smaller. Microchips, nanochips. We are reducing the size of the machine. Right? That is possible by this, which will be further amplified by this. Okay? Nowadays you take a photo, if you have a good resolution photo, that photo itself is 4 megabyte or 5 megabyte. Imagine in old days, 25 years back, nobody can store a photo. Because one floppy will be used. Okay? One floppy will be like 8, 10 or 20 pen drives, you put them together. So this is highly focused research area. Then come electronics. But these are two new phenomena slowly coming out in the market. I told you guys that something is called metal, something is called insulator, something is called semiconductor. So metal electrons can conduct. Insulator electrons cannot conduct. Can I develop a material where both electrons can conduct and cannot conduct? Yes. He's looking at me strangely. What the hell is it? Can I develop a material where electrons can conduct and cannot conduct? In last 10 years, people have defined and found out a new set of a new class of materials. Those are called topological insulators. What is topological insulator? Of course, you don't know. Topological insulator is such that if there is a compound, the electrons can conduct on the edge and on the surface. However, they cannot conduct inside. So they are insulated inside, on the edge of the surface, they are conductor. If those kind of materials can be two topotonics. Correct? Topotonics and valleytonics and many other stuff in this basket comes from certain other aspect of the solid. Okay? When I told you guys that I brought the atoms close to each other to form a solid, I didn't bother about how they arrange. All are come close, but do they arrange in a certain manner or they are so random? Okay. This brings the next component of solid structures. And all of you know, in your home, you always in mama's kitchen, you have a salt dabba and a sugar dabba. Yes or no? What are the distinction between them? Which is a crystal. This is crystal sugar, but sugar is not crystal. Salt is crystal, sodium chloride is a crystal. Okay? So, in solid, there are two classifications depending on the arrangement of the atoms of the molecules. One is called crystal, other is called amorphous. Sugar is amorphous. Salt is crystal. In crystal, what happens? The molecules or atoms, by the way, they have a new name in solid state physics. Don't call them molecule anymore. We call them bases. But forget that. Don't worry. Molecules are the atoms. They arrange periodically and with certain symmetries. In amorphous, they are so randomly arranged. Am I correct? So when the molecules or the atoms, they are arranged periodically with certain symmetry, there is new more constraints on the electron motion. So the electrons obey the symmetry, follow the symmetry. New invariances, new restriction, new conservation, all come into picture. In case of random arrangement, that is not the case. Okay, so the electron structure is very particular with the systems with crystalline structure. Again, crystalline structure has many symmetry aspects, which I will not go into the details in the class in this lecture because you guys are not yet mature to learn this. Okay, but this symmetry redefine the electron motion in such a way, by the principle in a defined way, which is not the case in the case of amorphous. Okay, so in the crystalline system, you don't have, you have certain restrictions and certain rules. One of the most popular rule is that atoms are periodically arranged, right? So you can see that identical surrounding around each atom. When atoms are periodically arranged, you can have two space. One is real space. Real space means what we see in the front of our eye. or we all are in the real space. Other is called reciprocal space or dual space or momentum space. Real space, reciprocal space, dual space, momentum space. Okay. This space defines these two new ideas, topotronics and bimetrics. But let's not get into the detail of those space. You will be confused. Already I have confused you. You will be confused more. Okay, all of you love to listen to the radio. No one listen to the radio anymore. If you go on a car drive with parents, they switch on the FM, you immediately say that please switch on the radio, isn't it? What is FM? What is FM? Let me try to understand. Frequency modulated wave. FM. All your transport you see using frequency modulation. Earlier, it was not the case. Earlier, it was amplitude modulation. AM and FM. So, amplitude is purely defined in one space. Frequency the reciprocal of that. So, like you have amplitude and frequency. Similarly, in anything you have a period. How does the frequency come into picture? If I say give an expression for the wave, what do you write? Sin omega t. Right? What is that omega? 2 pi f. F is the frequency. Right? In your wave you write a sin omega t or something. A stands for amplitude. Omega stands for angular frequency or frequency. Earlier the propagation was governed by A. That's why called amplitude modulated. Nowadays they are governed by omega, frequency modulated. And this A and frequency they form a dual space. You can define the same way using either of them. Similarly, in a solid, you can imagine A or the energy kind of forms in one space, either time forms in another space. Similarly, in crystals, there is a real space of arrangement. Since they are periodic, you can have a reciprocal space. Lot of things are hidden inside this physics of reciprocal space. In that reciprocal space, all these aspects people are now exploring. Okay, and this gives you the new age quantum electronics or called quantum technology. For quantum technology, you need quantum materials. What are those quantum materials? The quantum materials which are now defining the transport properties based on these factors. The whole idea of electronics are now classical because we have understood it. We have used it, we have exploited it. Silicon electronics has dominated the market. All our lifestyle is governed by that. But if you want to have higher efficiency, higher performance and those things, then all this newer mode of transport has to be explored. And they found quantum materials for quantum technology. So you are going to design new quantum materials, then you are going to create new quantum technology. By the way, our country has started something called quantum mission. Have you national quantum mission? National Quantum Mission. Under this National Quantum Mission program, researchers have been asked to come up with new quantum materials for next generation quantum technology, quantum transport. Our futures will be defined by that. Like the way I talk about electronics like a small thing, I mean already know. When you grow old, you will tell that, oh, this quantum technology is something. Then for you, I don't know what else will be. But research never stops. You learn new domains, new understanding, and new things. So solid-state physics is an exciting topic. Okay, it fuses a lot of subjects. Your quantum mechanics, electromagnetic theory, statistical physics, classical mechanics. All four of them come together, math physics all the time. Never forget math physics. It's father of all things. They have come together and they construct solid-state. Okay? So I hope I have given you a broader picture of what is solid-state physics, what is past, what is present, and what lies in future. Of course, each of them will take one lecture on its own. I could not teach in detail. I just gave you hints. Each of them take one lecture in own. The solid-state physics, as I course, have 5-6 subjects. There are 5-6 subjects on solid-state physics. Each are like 5-3 lectures. We cannot cover each of them. But I hope that you got a good understanding of solid-state physics. It should help you guys. And if any of you are interested to do future research or future study, right? Now you're too young to talk about this. Okay? But this is an exciting domain. All quantum technology defined by this. If you have any questions, I'd like to take. No question? So there are two things. Either you have understood or you have not understood at all. What is true? You have understood? I am still understanding. He has a question. Okay. What is the reciprocal space? Do you know Fourier transform? Somehow. Any functions u, if it is periodic, it can be defined u r as represent the real space is equal to summation of some g u g e to the power minus I g dot r. Any periodic function. Okay? Its period in R. Similarly, you can reverse it, you can calculate UG is equal to summation over G U R e to the power I g dot r. Something like that. And this G is called the reciprocal, from the reciprocal space. This G from the reciprocal space. I'm just saying that if R is the real space, G is the reciprocal space. Together they call dual space. One is real, other is reciprocal. We define them as real. In the reciprocal, this G will be defined. I put summation just for convenience, but you can integrate it and make G as a continuous vector. And that becomes a continuous space, and that's the momentum space or the reciprocal. In solid-state physics, you will learn. I think in class 2 you will not learn, but if any of you will pursue either engineering or basic science or something, in first year itself the teacher will teach you the reciprocal space. And like real space has symmetry and periodicity, The reciprocal space also has symmetry in periodicity. By the way, how many of you know lattice vectors and stuff? I am afraid of teaching those. That's why I am not teaching. Like each atoms are periodically arranged in a crystal, right? Each atoms are periodically arranged. Now you say that this repetition of atoms defined by the vectors. Okay. Since they are periodically arranged, their functions are also periodic. Since their functions are periodic, they can be expressed something like this. What is called Fourier transform? Okay. Since they can be expressed like this, they have a reciprocal. Okay. But don't try to think too much about it. There's a lot of math also involved. Which I have not.
So what would be reciprocal space of the physical? What would it be?
No, there is only one space. It can be manifested in another. That's called reciprocal space. Okay. In crystal system, this reciprocal space doubles up in explaining the momentum of the electrons. Electrons, kinetic energy, properties, and everything, it can explain. Okay. So, as I gave you the example of this frequency modulated wave and amplitude modulated wave, similarly, it's the example of real space or reciprocal space. Okay. So, if you know wave function, you know wave number. What is wave number? 2 pi by lambda. What is lambda? Huh? Oh, so I got the answer now. So what is lambda? What is 2 pi by lambda? Exactly. So imagine lambda is the real space and 2 pi lambda is the reciprocal. Either you define by lambda or you define by lambda. Okay? So you can explain properties either using lambda or 1 by lambda, no? Right? So your frequency is 1 by lambda. Anything else? Ah. Okay. In the beginning, we drew that phase diagram. I'll go back to the phase diagram. I said pressure, temperature, then say liquid, gas, solid, right? As long as pressure remains constant, temperature remains constant, that's called ambient conditions, right? The condition. Then the molecules of the system has one particular phase. Somewhere it lies here or here. Each of them is defined by your intermolecular sequence. Each of them is defined by intermolecular. So you make a freezing to melting. Only at this point you make a transition from one intermolecular separation to another. But in some cases, it is first order, means immediately it changes the intermolecular distance. Okay, so that's why we call that as long as the system is in the solid state, its intermolecular separation is this. It doesn't change. But the moment you make a change from one phase to the other phase, its intermolecular separation will change. But as long as it stays in the liquid state, its intermolecular separation will stay in that. Then you apply more temperature, it will happen melting, right? Melting means vaporization. Vaporization. then it will break out. Okay? So as long as that state is fixed, the intermolecular separation will remain intact. The system will keep on absorbing energy by applying pressure and temperature. At one point it will break. It will go to a newer state. Right? And newer state will have a newer intermolecular state. That's what Professor argues. Intermolecular force. No. It the intermolecular force, as I discussed, depends on the separation distance between the molecules or the atoms. That will change. That you cannot stop. Maybe he has talked something else which you could not understand. But all the interaction depend on the separation. That's why they are different. But okay, so there are some classical phenomena, there are quantum. The classical phenomena are little more different. In quantum phenomena, separations are very important. Classical phenomena, separation defines different kind of elasticity, mechanical properties, what you call it, right? So those depends on separation. Okay. Anything else, guys? So, how many days you have been here in the campus for RSIC program now? 5 weeks. How many? 5 weeks over. Wow, how many weeks left? After that, go home. 2 months. The school has started again. Good. I hope you are enjoying the campus. Good. If not, any more questions? There are no more questions. Shall we wind up now? Okay. Enjoy, all the best. Do well in life. My name, I told you to tell my name. Okay. I am Ranjit Nanda. I am a professor in the Department of Physics. Right? If you want to know a little bit about me, kindly visit this website, cmtcl-iitm.com. Okay. By the way, I have a bigger name, which is only a shorter name. So my real name is Birabar Ranjit Kumar Nanda. You visit my webpage to know more about. I do research on electronics. Okay. Also, to know more about in this area, how do people model atomistic modeling, we have a center. The center is called Center for Atomistic Modeling in Materials Design. Center for Atomistic Modeling. It's called CAMMD. If you are interested to know more about how people model atoms or materials, please visit https. What is this thing, right? Something like this. cammd.iitm.ac.in. So these two web pages will talk about. This will be my personal. This is about my center. They define the describe this using amplitude, how the amplitude get lost over distance. So you are at risk. When your teachers are important, and you always have distinction, right? What is the displacement? So the states cannot form in this way. Therefore, so in solid, they are allowed, they are all allowed, all allowed. So this will be perfect. No eigenvalues or eigen. No. All of this are the interactions that dictate about how the Hamiltonian is not as simple as eigen. It's always as beautiful. And it has something to do with the periodicity of the system. In the amorphous compounds, in the gap closes. In the periodic system, the gap amorphous the gap and so great. You have another lecture now? You have a break time. Project. What project you guys are doing? 16. Yeah. Okay, so have a nice day. Oh, this is for me?